To this point, we've learned a few new reactions, but so far we've only formed carbon heteroatom bonds. So things like CBr, CCl, C nitro, and the C sulfur bond. So how about carbon-carbon bonds? And that's one of the things that we want to learn about in this class. It is organic chemistry, so how do we form the carbon-carbon bonds which allow us to build complex organic frameworks? So the reaction to do this, this will be our fourth type of electrophilic aromatic substitution, which is the Friedel-Crafts reaction. And there's actually two variations of the Friedel-Crafts. We have an alkylation and an acylation. So first we're going to talk about the Friedel-Crafts alkylation. In the Friedel-Crafts alkylation, what we're doing is we're putting an alkyl group on the ring. An alkyl group is essentially some sort of CH group, like a methyl group, an ethyl group, a propyl. And we often just abbreviate that as R. So if you have R attached to your molecule, although we sometimes call that the rest of the molecule, R really represents an alkyl group. So for example, if you have RCl, this would be called an alkyl chloride. If you have ethyl chloride, the ethyl group is your alkyl group in this molecule. So let's take a look at this Friedel-Crafts alkylation where we put an alkyl group on the ring. And I'm going to start with benzene. And I'm going to use tert-butyl chloride as my alkyl chloride. Now, this also requires a Lewis acid catalyst. We use aluminum trichloride. It's very similar to the iron trichloride that we used before. And the product of this is going to be tert-butyl benzene. So all we've done is we've put this tert-butyl group on the aromatic ring. So let's work through the mechanism of this one. And this one's going to be kind of similar to some of the others that we've seen because we're using the Lewis acid. So the first part is again going to be generation of our active electrophile. And I'm going to use tert-butyl chloride and our Lewis acid. And a lot like we did with the bromine and iron tribromide, the halogen, one of those lone pairs, will add to the metal. This will give us our Lewis acid base adduct. We get a negative on the aluminum, a positive on this chlorine. From here, and this step can kind of vary depending on what alkyl group you have, but we're going to try to keep it as simple as possible and just always think of this as going ahead and losing this group to give you a carbocation. So here we have the tert-butyl cation. and AlCl4 minus. So now this tert-butyl cation is your active electrophile. That's what will react with the benzene ring. Now, in the second part of this reaction, we're going to take benzene, and this part should be getting really familiar to you by now. All we've been doing is just changing out the electrophile that we're using. Here is our carbocation electrophile. We'll use the pi bond, react with that. That puts the tert-butyl group on the ring. We still have the hydrogen there. And then we need to regenerate our Lewis acid. So let's use the aluminum tetrachloride. And we'll lose a Cl minus from that, which will come over and grab the hydrogen to give us HCl. And those electrons will come down to form the pi bond. There's HCl. There's our Lewis acid regenerated. Unlike some of the other EAS reactions, the Friedel-Crafts alkylation is a little bit more finicky. There's some things we have to concern ourselves with in terms of, will it work? Will it work the way we want it to work? So we're going to look at some features and limitations of the Friedel-Crafts alkylation. So the first thing just has to do with what type of alkyl chloride can you use? And in this case, we can use methyl, primary, secondary, or tertiary chlorides. So the scope there is pretty good. I will mention here for accuracy that it's thought that the methyl and the primary substrates don't actually go through a discrete carbocation intermediate, meaning a full true carbocation. But when we draw out the mechanisms for these, we're going to show it as a carbocation, just to help us keep track of where the electrophilic atom is at. The key, though, is that for the alkylation, the alkyl chloride carbon must be sp3. Again, we're talking about the alkylation. So, for example, if you have an sp2 carbon, like we have right here, that's not going to work in the Friedel-Crafts alkylation. If we have a triple bond with an sp hybridized carbon chlorine bond, that's not going to work. You need an sp3 hybridized carbon here. Now, it doesn't matter if you could potentially have an sp2 carbon somewhere else, but the carbon bonded to the chlorine must be sp3. The third thing, which is an important thing to keep in mind, because if you forget about this, you can end up drawing the wrong major products. It's just that since we are dealing with carbocations, remember back to organic 1, carbocations can and will rearrange to become more stable. So you have to account for that. So let's take a look at an example, and say we take benzene plus isobutyl chloride, and if you use this, chances are, just without thinking through the mechanism, what you might expect is for this isobutyl group with this carbon right here attached to the ring. So this is probably what you would expect. But the actual product you get is instead tert-butylbenzene. So why do we get this product? Well, because the carbocation intermediate you get rearranges. So let's think about that in terms of the mechanism. So in the first step, when this chloride binds to the Lewis acid, you get this adduct here. And then if you think about this in terms of the original mechanism, and we draw out a carbocation forming here, that bond breaks. You get this carbocation. So here you have a primary cation. Well, remember carbocation rearrangement, that will rearrange to become tertiary. So you have this hydrogen right here that's implied. That will do a hydride shift. And when that hydride shifts over there, what you get is this tertiary cation, which is more stable. And that acts as the electrophile. So that's what reacts with the benzene to give you that product. So that's something you always want to just be aware of and just be on the lookout for. So anytime you do these reactions, I encourage you to always think through the mechanism, draw the Lewis acid base adduct like we did here, break that carbon-chlorine bond to give the carbocation, and see if it might rearrange. If it can rearrange to become more stable, it will, and that more stable carbocation, it's that carbon, which is this one right here, that bonds to the benzene ring. The final feature has to do with if you have something other than benzene, like a substituted benzene reacting under a Friedel-Crafts reaction. This reaction is a bit finicky, and certain groups will prevent the Friedel-Crafts reaction from occurring. So there will be no reaction if an amino group is on the ring, or a strong electron-withdrawing group. If either of those are on the ring, the reaction won't take place. So remember the amino, it could just be NH3, or it could be NR3, it doesn't have to be hydrogens on it. A strong electron withdrawing group, these are something we're going to go over extensively a little bit later on. We've talked about a few of these, but just to give you an idea, some things to look out for. A nitro group, a carbonyl. It's not as strong as the nitro, but it's still fairly strong. Sulfonic acid group, cyano group, those are all fairly strong withdrawing groups. Those prevent the Friedel-Crafts reaction from taking place. So just to give you an idea of what I mean here. So let's just say, for example, you have tert-butylbenzene. And you want to put an ethyl group on that ring as well. So you use ethyl chloride, aluminum trichloride, and later we'll talk about why the ethyl goes where it does on this ring. But what happens is this reaction works just fine, and the ethyl group actually ends up para to the tert-butyl group as the major product. And this works well. But if you use an amino group or a strong electron withdrawing group, the reaction doesn't take place. So why is that? Well, the amino group, the problem with it actually lies in the lone pair. And actually, let me fix a mistake up here. This should have been NH2 and NR2. But if we take this amino group and say you want to use ethyl chloride and aluminum trichloride, the problem, instead of, what you want to happen is the chlorine reacting with the Lewis acid. Well, the lone pair on the nitrogen is a better Lewis base, and it instead reacts with the aluminum trichloride. And you end up with this Lewis acid base adduct. And basically your catalyst is tied up, and that shuts down the reaction. Now, in the case of the strong electron withdrawing groups, these will prevent the reaction as well. So again, let's say you use ethyl chloride, aluminum trichloride. These groups are deactivating groups, and they deactivate the ring. So you get no reaction here because this deactivates the nucleophilicity of the ring so much that the reaction can't take place. And it's just a fact of the Friedel-Crafts reaction being kind of difficult. So these withdrawing groups are not problematic for the other electrophilic aromatic substitution reactions. It's just the Friedel-Crafts reaction where they're problematic. The fifth and final reaction we're going to use to put groups on the aromatic ring is a different variation of the Friedel-Crafts reaction. It's the Friedel-Crafts Isolation. An acyl group is this carbonyl with a carbon attached. So if you see this attached to something, that's an acyl group. If you have this chloride, that's an acyl chloride. So the acylation puts this entire acyl group on the ring. So here's an example of that one. Here I'll use benzene and this acyl chloride. And these are some of the easiest to predict. And we'll see why when we look at the mechanism in a second, but you don't have to concern yourself with carbocation rearrangement in the acylation. In this case, we will directly put this acyl group on the aromatic ring, and the carbonyl carbon is what will be attached to the aromatic ring. So here's our product. There's the carbonyl carbon attached to the ring, and this group that I highlighted in green directly attached. So let's go through the mechanism. And it's very similar to the Friedel-Crafts Alkylation in terms of the electrophile generation. So I'm going to use my acyl chloride, AlCl3. The lone pairs on that chlorine, those will bond to the aluminum. And we get the bond there. A minus on the aluminum, a positive on the chlorine. And just like we did before, we're going to lose this chlorine to form a carbocation. But it's a little different than the carbocation we had before. In fact, on first glance, it may not even look that good. Because what we get is this carbocation on a double bonded carbon. And usually we say that's a bad structure. But in this case, that's not really so, because despite having that double bond there, unlike just a carbon-carbon double bond, this oxygen has lone pairs. And through resonance, we can remove those lone pair electrons, generating a resonance structure here. And this carbon actually is sp hybridized, so I'm going to draw it linear. Like that. So this resonance stabilized carbocation will not rearrange. So you don't have to worry about that. Now, although you have both resonance structures here, this resonance structure is the easiest one to work with for the next step, because that's the carbon bonding to the aromatic ring. So now we can take benzene like we've done several times already. There's our electrophilic aromatic substitution. Then again, I'll use this aluminum tetrachloride to act as the base. There's our product, and our byproducts HCl, and aluminum trichloride regenerated. So in terms of the features, you need the acyl chloride. You don't have to worry about rearrangement, but like the alkylation, this reaction is also kind of finicky in that this reaction won't work if an amino group or strong electron withdrawing group is on the ring. So just be aware of that when doing either of the Friedel-Crafts reactions.